Okay, let's get started. So, so, uh, so I posted the lectures, no, the lecture video, in the previous week. Okay, and then I hope everyone watched the lecture video. So in the previous lecture, so I explained about the data forwarding unit in the pipeline architecture. So we are going deeper into the pipeline architecture. Okay, so actually the pipelining concept, the concept is not difficult, right? So the concept is just simple. So we can divide some required steps into the the multiple parts, the multiple stages, and then for each clock, for each clock cycle, then we can make the instruction or task propagate the multiple stages. Okay, so this is the concept of the pipelining. But I mentioned we also need to consider the performance issues in the pipeline architecture because of hazards, right? So I explained that the clock cycles can be wasted because of hazard, right? There are three types of hazard: the data structure hazard, data hazard, and then control hazard, right? So and then we need to handle this performance issue caused by hazard. So in the previous lecture, so we learned about the data forwarding unit. Okay, then how to implement, how to design data forwarding in the pipeline architecture. So as you can see in this slide, so you can find the forwarding unit. So it is because the forwarding is, but the data forwarding is controlled. Data forwarding is performed in the EX stage, right? So in the EX stage, we just compare the destination register of the current instruction and I don't know, source registers of current instruction and destination registers of previous instructions, right? And then the forwarding, the data is forwarded into the input of ALU. So that's why the forwarding unit is here. And then we also learn the data forwarding conditions, right? How to decide the selection signals for these data forwarding multiplexers, right? So that's what we learned in the in the previous class. So we need to also consider the priority. Okay. So for this case, so this case shows the double data hazard case, right? And then we know, so we know that the latest result needs to have higher priority because this is the latest value for this this current instruction, right? So that's what we learned, and then the voting is here. So now, so we will learn how to implement the load use hazard. So load use hazard handling. Okay. So what is the load use hazard? If the previous instruction is a load instruction and then the destination register is updated by this load instruction. And the very next instruction demands the result from this load instruction. This is the load use hazard, right? So I explained that we cannot avoid this data hazard, right? Because the load instruction create the result value in the memory stage, right? But this result needs to be this result is required in the EX stage, right? So So in this case, the next instruction, the following instruction needs to be stalled. So which means that the following instruction needs to wait for one cycle in the ID stage. So why ID stage? So you can find the the for the load used hazard can be detected in the ID stage. Then why? Why ID stage? So the instructions are fetched in the instruction fetch stage. Okay, so we can get the instruction in the late part of the clock cycle in the instruction fetch stage, and then this instruction is propagated to the ID stage, and then by decoding the instruction field or instruction data, we can figure out the instruction type and then source registers, right? So actually in the ID stage, we can figure out the instruction type and then the source registers. So we can also detect the load use data hazard in the ID stage. Okay. So then how can we detect? So this is similar to the data forwarding unit, right? So what is the condition of data forwarding? If the destination of previous instruction is equivalent to the source registers, the one of source registers in the current instruction, then we need to perform data hazard usually. So for normal cases, right? So this is the same, right? So how can we detect the load use hazard? So what is the condition for this load use data hazard? So firstly, the current instruction is the load instruction. No. The previous instruction, sorry. Why? The previous instruction is load instruction. Okay. And the following instruction receive the data from load instruction, which means that the RS1, and RS2 of the current instruction is equivalent to the RD of load instruction. Right. So actually the load use hazard is simple, right? So firstly, we need to detect the load instruction. So load instruction, then we can detect the load instruction with the mem read signal, and then we need to compare the previous example and then current example, and then I mentioned that the current example is in the ID stage, right? So and then the mem read, this is the previous instruction. So previous instruction is in the EX stage. So you can find the ID/EX. So what does that mean? So this is the pipeline register, and then the mem read is the output of this pipeline register. So what does that mean? This mem read signal is in the EX stage. So if the mem read signal in the EX stage is 1, so which means the instruction in the EX stage is also load instruction. So this is by using this signal, we can detect the load instruction. Okay. And then we need to compare the RD of load instruction, and then RS1 and RS2 of the current instruction. So you can find the ID/EX, so which means that this is the RD in the EX stage, right? And then you can also find the instruction fetch slash ID. So this is the RS1 and RS2 in the ID stage, right? So if the current instruction is in the ID stage, then we can just compare the RS1 or RS2 of this instruction, the current instruction, with the RD of the previous instruction, like previous load instruction, right? So this is this condition for load use data hazard, right? So uh, so we can also uh, check some special cases such as if the RD of the load instruction is 0, then we need to so this means that the register this RD is not updated by load instruction. So then we don't need to check the load use hazard. But this is some usual conditions, the common conditions for the load use data hazard, right? So if this load use data hazard is detected, then we need store. So store means that so instruction in ID stage, right? The instruction in ID stage stay in the ID stage for additional 1 clock, right? This is the pipeline stall by load use hazard. So I will repeat. The instruction in ID stage stay in this ID stage for additional 1 clock cycle. This is the pipeline stall. So instruction can be stored, but then for the next clock cycle, then what will happen in the EX stage? So it means the instruction will stay in the ID stage, right? Then for the next clock, then what will happen in this EX stage? So the load instruction will be propagating to the memory stage, right? Then how about the EX stage? So EX stage actually, so in the EX stage, so this processor does nothing, right? Do nothing. How? So this is called the bubble. So okay, so you can find the bubble here. So if a pipeline stage does nothing, then we call this is a bubble, right? So and then how can we implement bubble? So I explained that if an instruction is uh, an instruction is executed, then what is updated? Architectural states. Architectural states means that registers and memory, right? And then we can control these update processes using control signals, right? So it means if we just set the reg write is 1, then register is updated. And then if we set the the mem write as 1, then memory is updated. So using the control signals, we can control the updates of the architectural states. So it means if we just make all control signals zeros, then we can make a bubble. So nothing, okay, do nothing. So how to store? How can you store the pipeline? Firstly, the instruction stays in the ID stage, and we can just make bubble. So bubble is also called the NOP, NOP, and then this NOP represent the no operation, right? So we can just make the no operation. So it means this instruction does nothing. Okay, and then we can make the all control signals zeros. Okay, and then the instruction stage in the ID stage, and then if the instruction stage is on the current instruction stays in the ID stage, then the instruction in the instruction fetch stage also stored in the instruction fetch stage, right? Because the previous instruction stays in this stage, then the following instruction cannot propagate in the next stage. So how can you make how can you implement the pipeline store in the instruction fetch stage? We can just maintain the PC value, right? The PC is not updated. So in order to fetch new instruction, right? In order to fetch new instruction, we need to update the program counter. But if this program counter value is not updated, then the same instruction will be fetched from the instruction fetch stage. So, which means we can make the instruction stage in the instruction fetch stage by making by maintaining the EPC value in the instruction fetch stage, right? So two instructions stays in these instruction fetch stages and the instruction ID stage, and then the bubble is generated for EX stage. So we can make the all control signals of EX stage as zero, right? And then the previous instructions, like the load instruction, the the load instruction, and then the previous instruction are propagated in the memory stage and then write back stage. Okay, so this is how to implement the pipeline stall by load use hazard. So you need to understand how to implement. So firstly, make the all control signals zero in the EX stage, and then instructions stay in the ID and instruction fetch stage, right? So this is this figure shows how the instructions are stored. Instruction is stored by load use hazard. So you can find that this previous example is the load instruction, and then the bubble is generated. So in CC3, the clock cycle number 3, so you can find that the load is here, and then actually the end is in the ID stage. So actually you can, so this pipeline diagram just shows how the instructions are flows, but actually, so in this situation, the end is in the instruction. No. So when the load is in the EX stage, the end is in the ID stage. Okay. And then, so you can find that actually the end is here. And the bubble, and when the load instruction is in the memory stage, and then you can find the bubble. The bubble is here, and then the end instruction is still stays in this ID stage. So it just represent the it is equivalent to the nope. Nope instruction is inserted to avoid the load use data hazard. But so just to show the timing of this pipelining operation. Okay. Or you can understand that if the the pipeline is stalled and then loop is inserted, and then when the end instruction is in the EX stage, then the fetched result can be forwarded to the EX stage. Okay. So this is the load used data hazard. So then how can we implement this data hazard? So in order to implement the data forwarding, we implement the forwarding unit in the EX stage, right? So because as I mentioned, the data forwarding is detected when the current instruction is in the EX stage. So the forwarding is detected in the EX stage, which means the data forwarding unit exists in the EX stage. And then I explained that uh, load use data hazard. Load use data hazard needs to be detected in the ID stage. So you can find the hazard detection unit. So this is called the HDU, the hazard detection unit. So hazard detection unit exists in the ID stage. Okay. Then what are input signals? What are input signals of this hazard detection unit? So as I mentioned, we need to compare the RS1 and RS2 in ID stage, right? And then what are other inputs? You can find the mem read signal. So, but this mem read signal is from the mem read signal is in the EX stage, right? So you can find this control signal, mem read signal comes from the ID/EX pipeline register, right? And then also we need to check the RD, but RD in EX stage, right? So by doing this, so we can check the load use data hazard, right? Then what are output signals of this hazard detection unit? So what is required? So what is required? So firstly, so we need to make the bubble, okay, and then make ID and instruction fetch stalled. Okay, those are required actions by load use data hazard. So how can we make a bubble? We can make all control signals 0, right? So you can find the multiplex here, and then if the hazard is detected, right? If the hazard is detected, then this is selected. So all control signals become zeros. So in the next cycle, the instruction in EX stage becomes the bubble. It means nope. And then, so we make the instruction stay in the ID stage and then instruction fetch stage, right? Then how? So you can find the instruction fetch and ID write signal. So which means, so actually you can just understand that this signal is the enable signal. Okay? So which means if the pipeline registers are enabled, then this D flip-flop, so the pipeline registers are D flip-flops, and then these D flip-flops sample the value from the input port, and then this sampled value is propagated to the output port of D flip-flop on the rising edge of clock. Okay, this is the operation of the D flip-flop. So if you can find this is the instruction fetch and ID write, so you can just understand that this is the enable signal, right? So if we just make enable is 1, then the data in the data of the input port is propagated to the output of this pipeline registers. Okay. Then if we just make this enable signal 0, then the value is not updated to the output port of the pipeline register, right? So if the input value is not updated, then the signal, the instruction has the all signals in this ID stage are maintained, right? Do you understand? So we can just control the enable, the right enable port of this pipeline register. So okay, so by making the enable signal 0, then the instruction stays in ID stage. Okay. Now how about the instruction fetch stage? You can find the PC write. So you can also understand that this is the PC enable. Okay. So if the PC is updated, then the new we can fetch new instruction. But if the PC is not updated, we can just fetch the same instruction, right? So by making this write signal 0, so PC enables 0, then the PC is not updated. So the instruction in instruction fetch stage also is maintained. Okay, so these are required operation, required output for load use data hazard. Okay, so output from the hazard detection unit. Okay, so by doing this, we can control the load use data hazard. Okay, so and then we already learned that the data hazard cause performance downgrade. Okay, and then we can just avoid. We can just handle these performance drop issues using the compiler technique. So we already handled this issue, right? So I will skip this slide. Okay, so in the pipeline architecture, so we learned how to implement data forwarding and data hazard, the load use data hazard, right? And then now, so we need to handle control hazard. Okay, so what are control hazards? If the clock cycles are wasted by control signals like branch instructions, then so we can call this is control hazard, right? So this is the example. So if the branch outcome determined in memory stage, so actually in the single cycle processor design, so we assume that in the BQ, the result of a BQ instruction is determined by ALU, right? We can just compare the two source registers using ALU, and we can apply the sub operation in ALU. So which means in ALU, the one clock cycle is taken. right? For the branch instruction. And then this result needs to be propagated into the memory stage, and then this result is given to the PC, right? Do you understand? So the result of branch instruction is updated when this branch instruction is in the write back stage. Do you understand? So I will explain. So this is the example. So you can find that BQ is here, right? The branch instruction is in the here, and then these are next instruction. What is this number? This number is PC, right? So when the BQ is taken, so if the condition of this BQ is true, then this is the target. So we need to fetch this load instruction. But I explained that the BQ, the condition of BQ is compared, okay? The two source registers are compared by ALU, but with the ALU, the 1 clock cycle is taken, okay? It's because of the delay of ALU. So actually, the result is given to the memory stage, okay? And then we can use this result, the result of the branch instruction. So if the branch is BQ is in the memory stage, then these instructions, the next instruction, the AND instruction, OR instruction, and ADD instruction are in the, so AND is here, OR is here, and then ADD is here when the BQ is in the memory stage. And then we detected, the processor detects that, BQ is true, okay? So which means that the zero, the zero output of this ALU is 1, okay? So using this true condition, then the branch is given to the AND gate, and then this is given to the multiplexer of the PC, right? And then the target of this branch instruction is given to the PC, right? When the branch instruction is in the memory stage. Do you understand? Okay. So it is because all hardware components exhibit delays, right? So you need to understand how the signals flows the data path element in the pipeline stages. So as I explained, the result is here, and then result is ended, and then the condition is given to the multiplexer, PC multiplexer, and then the updated target is given to the PC, right? So this PC value is the next PC, right? And then so currently the add instruction is in the instruction fetch stage, right? So when the branch, so in the next cycle, when the BQ is in the write back stage, then using this PC, the target of a branch instruction, we can fetch correct instruction. Okay. So load instruction is in the instruction fetch stage. So you can find the PC is here. Okay. So this PC is the correct PC, the target of a branch instruction. Okay. Using this PC, then load instruction is fetched. Then we can observe that, these instructions are incorrect instructions. right? Because the branch is, the condition of a branch is true. So, and then we observe that the incorrect, so three instructions and or add instructions are still already in the pipeline stages. So if we do not cancel these instructions, then what will happen? The computer, the processor will generate the incorrect result, okay? Because of incorrect instructions. So we need to cancel, these instructions, three instructions. So which means three cycles are wasted because of taken branch. So taken branch means that the condition of a branch is true, right? So the processor needs to jump to the target of a branch. So which means the branch is taken. So, and then we can just, so in this case, so these instructions are just canceled. So how can we implement this operation? So as we learned, by making all control signals zeros, we can cancel these instructions, right? So when the BQ is here, then we can just make the control signals in memory stage, and then the EX stage, and then also the ID stage, all zero, right? Then we can cancel these three instructions, okay? So this is the branch operation. So it's a normal branch instruction. And then also you can observe that three cycles are wasted. Then how can we reduce the performance drops by branch instructions? How? So what's the problem? What's the problem of control hazard? Why three cycles are wasted? It is because the branch outcome is determined in memory stage. So which means the branch condition is determined late. So if there are more stages before this branch uh, resolution, so which means that the result of a branch is reserved, then the processor will waste more cycles. But in the pipeline, this simple five-stage pipeline architecture, the branch is determined in memory stage. Then, so the three instructions in EX, ID, and instruction fetch stages are cancelled. Okay. So, and then problem is that because the branch is reserved, the branch is determined late, so many cycles are wasted. Then how can we solve this issue? If the branch is reserved earlier, then we can reduce the performance drops. So we can reduce the number of cancelled instructions by taken branch. So this is some example. This is the example, right? And then actually in this course, so we are just implementing the processor that supports only BQ. Okay. So BQ just check the RS1 is equal to RS2, right? So this is checked by BQ. And then actually we just use the sub operation, the subtraction operation for checking the equality of RS1 and RS2. But actually, we can just implement the very simple equality check logic. How? So actually, if we just use the sub instruction, right? Sub instruction is just the adder, right? Okay. So and then we can make the faster adder, but usually in the adder, the carries are propagated to the next digit, and then the delay is increased by the number of this digit, right? But actually, if we just want to check the equality of the two bits, then we can use exclusive OR gate. Why? In the exclusive OR gate, so this is the A, B, and then this is the output, 0, 0, 0, 1, 1, 0, 1, 1. What is the output of the exclusive OR gate? This is 0, 1, 1, 0. So you can observe that if the two inputs are the same, then output of exclusive OR is 0. And then if the two inputs are different, then the output of exclusive OR is 1. So actually using the exclusive OR gate, we can actually compare the two input bits, two input bit signals. Okay. So because our processor just supports the PQ, then we don't need to use the subtractor. Okay. And then we can just use the exclusive OR. Then how? So this is the RS1 0, and then RS2 0. Okay. So what is this? This is the pin number of the RS1 and RS2 signal, and then we can apply the exclusive OR gate, right? And then this is the some output of this exclusive OR gate, right? And then we can just apply the exclusive OR gates to the other bits like RS1 1, then RS2 1, pin number 1, and then exclusive OR gate. Then if the one of these value is 1, then it means this is different. Two values are different. So using the large OR gate, so actually there are many bits, more bits here. So using the OR gate, then we can detect that, oh, if the two values are different, then it becomes the 1. Okay. So in order to check the equality, then we can just use the NOR gate, right? So which means if the two values are equivalent, then it becomes the 1. Okay. Right. So actually, we can make very simple equality check logic using the exclusive OR gate, and then by ORing the result of this multiple exclusive OR gate. So if you see that this hardware, so actually there is no carry. There is no carry propagation in this equality check logic. So you need to understand the delay of the hardware, right? So, but you can just check that actually these operations, the equality check for each bit can be performed in parallel, right? There is no propagation. So the the performance issues in adder is the propagation of carry bit. So if you took the digital logic design course, so actually, so I believe you can understand this issue. But so which means because the carries needs to be propagated into the next digit, the delays are increased. So actually the ALU or adders just take the one cycle, right? One cycle in the pipeline architecture. But the equality check is very simple because all bits we can just apply exclusive OR gate for each digit, and then this operation can be performed in parallel, right? So in parallel means that at the same time, the bit equality check, the equality check can be performed for each bit and then ORed, which means the delay of equality check is very low compared to the subtractor. Okay, that's what I want to say. So you can find so we want to make the branch instruction reserved earlier, right? And then when the branch instruction is executed, then branch instruction reads source register values RS1 and RS2 from the register file in ID stage. You can find the equality check logic here, okay? Just after the register file. So, and then as I mentioned, the delay of equality check is very low, right? Then we can simply add this equality check in the ID stage. So which means the branch is determined in ID stage, not memory stage. So original branch was determined in memory stage, but by adding the equality check logic just after the register file, we can make the branch determined in ID stage. Then what is the benefit? Because the branch is reserved in ID stage, the earlier, then when the branch is taken, only one cycle is wasted. In the original design, the branch was determined in the memory stage, so 3 cycles are wasted if the branch is taken. But in the new design, the equality check logic is here, and then the branch is reserved early, and then this is given to the PC mux, the multiplexer for program counter, and then target. The target of a branch is just given to the next PC of the PC register. And then the next clock, this PC can be updated here, right? Then the next instruction can be fetched. So when the branch is taken, the instruction in instruction fetch was just cancelled. We can just cancel just one instruction. Okay? Do you understand? So you can just understand like this. If the branch is determined in memory stage, then there are 3 instructions, right? And then this result, the result of a branch will be reflected when the branch is in the write back stage. And then because the branch is determined in memory stage, there are three incorrect instructions in this pipeline processor. And then if the branch is determined in the ID stage, and then which means there is one incorrect instruction in the instruction fetch stage. So we need to cancel this one. So only one cycle can be wasted. Okay. So this figure shows the enhanced. So which means that the performance drops by taken branch is just so it's just decreased. So it's handled. So when the branch is in the ID stage, and then this is the incorrect instruction, the end instruction, and then these are the previous instructions. And then next cycle, the branch is here, and then the target can be fetched. So, and then I mentioned that this instruction is the incorrect instruction. So we can make a bubble in the ID stage. Okay. And branch is here. Then the previous instructions are here. Okay. So do you understand? So try to understand. So actually try to understand the timing of this branch instruction. Okay. But so actually, so this is but I believe I don't believe this is a good approach. So it is because actually using this equality check logic, we can just support the BQ and BNE only, right? So, there are two different instructions, two different branch instructions, such as BLT and BGE. We cannot implement BLT and BGE using equality check logic, right? So because the BQ, we can just check the equal. BNE, we just check the not equal, but BLT, we need to check the less than. BGE, we need to check the great or equal to. We can support the BEQ and BNE using equality check logic, but we cannot support the BLT and BGE using the equality check logic. So in order to check the BLT and BGE, we need to use the subtractor, right? And then another issue is the new data hazard. So what does that mean? So where is the data forwarding unit? The first question, where is the data forwarding unit? In EX stage, right? So which means, so the forwarding unit is in the EX stage, okay? Which means the forwarding is checked in EX stage, right? Then what's the problem? BQ is determined in ID stage. And then, which means the BQ needs to receive two source registers from register file, right? So So how can you implement the data forwarding? The ALU receives the source register value from the other stages, not register file, because the register file will be updated in the write back stage. It's too late, right? So in the forwarding unit, the ALU receives data from other stages, not register file. But this architecture, in order to check the BQ receives RS1 and RS2 from register file only. What's the problem? The problem is that before the RS1 or RS2 are updated by previous instructions, then this PQ cannot be performed. Do you understand? Do you understand? So how can you handle the data forwarding? So the data forwarding mux is in the EX stage. Then switch means the data is given to the ALU from the other pipeline stages, not register file, because a register file is updated in the write back stage. But BQ just use the data from the register file, right? So we cannot, this BQ cannot use the data forwarding, right? So this case, so this is the, where is the BQ? The BQ is here, and then you can find the add instruction is here, right? And then the add instruction updates the X4, and then BQ use the X4. So in this case, the BQ needs to wait until this add instruction updates the X4 in the write back stage. Okay. So actually the actually the win the if the this one, so by adding this the equality check logic in the ID stage, so we can just reduce the theoretically we can reduce the clock cycles. The clock cycles waste by taken branch. But actually, because of this issue, the new data hazard, right? So we can also observe the performance degradation issues by branch instructions. Okay. So actually, I don't like this design. because so if you read the textbook, you can also find the equality check logic. So the starting point. So starting point is that we need to determine the result of a branch instruction early and earlier. Okay, in order to reduce the performance drops by control hazard. So approach is actually good. In order to reduce this control hazard, so in order to reduce the performance drops by control hazard, we need to determine the result of a branch instruction earlier. So we can use the equality check logic in the id stage. So approach is good. Okay. So we just analyze the causes of the performance drops. Okay. And we just observed that the branch is reserved very late. So we need to make the branch instruction reserved earlier. So it's in the id stage. But another issues, we can just observe another issues is the data hazard. Okay. So actually, so I don't like this operation, this approach, right? But if you read the textbook, then you can find that the textbook also, actually, this is the slide from the textbook, okay? So textbook just applies this approach, right? So then what's the problem? So problem is that the branch instruction cannot utilize the data forwarding, right? So in order to utilize the data forwarding, then the branch needs to be determined in the EX stage. So instead of this approach, so we can just make the dedicated branch unit. Okay. So this you can find the 5-stage pipeline architecture here, but you can find that the branch unit is here. Okay. So and then I mentioned that in order to support the 4 different branch instructions, we need to use the sub. Okay, subtractor. And then the good thing is that if we just implement the subtractor, then we can just implement the fast subtractor. Okay. So actually we can make the dedicated branch unit in the EX stage, right? And then this dedicated branch unit receives the forwarded value, like the ALU, can receive the forwarded value from the data forwarding multiplexers. Okay. And then we can calculate the result of a branch instruction earlier in EX stage. Okay. So branch is determined in EX stage by this branch unit. So in this case, if the branch is taken, then 2 cycles are wasted. If the branch is not taken, then there is no penalty. But this is better. I think this is better design. Okay, because in order to support this design, then we need to also consider the additional data hazard. And then I believe this data hazard can be also observed frequently in the normal code. So I mentioned that the data dependencies are observed frequently in our normal code, right? So, and then this can be observed also frequently. And then, so, which means that actually the data forwarding is not handled by these branch instructions, then the clock cycles are wasted because of this data hazard, regardless of the result of branch instruction. So I think this is not efficient. This is not efficient. Okay. So actually, so this is, I think, I just believe this is the better design. So branch unit is here. This is the dedicated branch unit. So this branch unit received the forwarded data in the EX stage, and then which means the branch can be determined in EX stage. And then these are penalty. The branch is taken, then 2 cycles are wasted, and branch is not taken, then no penalty. we don't need to cancel the previous, no, we don't need to cancel the instructions in ID or instruction fetch stage if the branch is not taken, right? So we can just add the comparison unit in the EX stage. So actually, in the lab, the last lab, you will be requested to implement the pipeline architecture. But and then actually in the pipeline architecture, so the the, the tricky part is to the implement the boarding unit and then hazard detection unit. So hazard detection unit includes the load use data hazard and control hazard. Okay, but the in the final lab assignment, then you can just implement the branch instructions like this, the control hazard like this, which means the branch is reserved. The branch is determined in the EX stage using the dedicated branch unit. Okay, not ALU. So, so this is the control hazard by branch instruction. And then, so actually, this is the kind of branch prediction. So why? So actually, in order to reduce performance drops by the control hazard, we can just exploit branch predictor. So what is the why? So I explained that the performance drops by the branch instruction is caused by the timing of the branch the branch result. So it means that the branch is determined late. Okay, so which means that in order to reduce the performance drops, then we need to reserve branch earlier, right? But so we can make the dedicated branch unit in the EX stage, and we can reduce the one cycle. And then also this is kind of a branch prediction, so, which means that we just predict that the branch is not taken, right? Because so we just fetch the next instruction using the not taken branch. So it means that we just fetch the next instruction using the PC plus 4. Okay. So this is the static branch predictor, and then in the static branch predictor, we just predict that the result of branch is not taken. But if the branch is taken, then 2 cycles are wasted. How can you reduce this wasted cycle? So we can also apply branch prediction technique, right? Why? I mentioned that because the branch is reserved late, then more cycles are wasted by take branch, which means if we figure out the result of a branch instruction earlier, right? I mentioned figure out, which means if we predict the result of branch instruction earlier, then if the prediction hit rate is high, we can reduce the performance drops. Performance drops by branch instruction. Do you understand? So in the pipeline architecture, we can apply the dynamic branch prediction. Okay, so it's just the prediction. So actually, in the previous, so in the original design, we just predict that branch is not taken always. Okay, so it's not prediction. This is not dynamic prediction. But problem is that if the branch is taken, there's 2 cycles are wasted. So we want to reduce this wasted cycle. So we can predict the taken branch. So which means the result of a branch instruction in runtime. So dynamically, which means a processor just predicts the result of a branch instruction dynamically in runtime. Okay, this is the dynamic branch prediction. So we will learn about the dynamic branch prediction in the next class. Okay, but in the control hazards, just to remember that. So because the branch is reserved late, so the performance drops by control hazard are increased. Okay, so we can just make the branch is reserved earlier. Okay. Okay, so I'll stop here. Any questions? Okay, thank you for your attention and see you in the next class. 감사합니다.